Welcome again with me, Paul Tapanca dan Sumarang. In this mobile game development, I will explain to you about learning from the master part 1. Okay. When a character is shot in a game, they collapse like a ragdoll. This effect can be simulated using the Ragdoll feature of Unity. In the star function, we create a green base cube. Then we create the red capsule body. We add a rigid body component to allow it to fall. Finally, we use add relative function to attach a head to arms and to legs. The first argument to add relative is the game object, which we will create a spare relative to. For example, the capsule body. The x-rel and y-rel argument determine where the new spare will be located. For example, x-rel equal 1, y-rel equal 2 will create a spare to the right of the original. The final argument determines the scale of the new spare. We scale and locate the new spare. Some random Z translation is included to allow the ragdoll to collapse differently each time. We add a rigid body component to apply physics. Finally, we attach the new spare to the original, for example the capsule body, using a character join. Run and watch the ragdoll collapse. Rerun. In this game, you will drag the mouse or your finger to shoot ball at the blue target. To start, we create the blue target ball. One red shooting ball is spawned now. Star POS is the screen coordinate of the ball being shot. Star POS is set coordinate according to either the begin event of a touch or the mouse down event. To avoid index error, we check touch count before accessing get touch. Pause is the screen coordinate of where we release the ball. This will either be the mouse position on a mouse button up event or a touch position on ended event of a touch. Once a move has been detected, we obtain the ball being shot or hit. We find the word coordinates of star POS or SV and POS FV. We'll calculate the direction and strength factor or dir. We add a force to the ball being shot and spam a new ball to shot. Excuse the messy code, it's been hexed to fit on a single slide. Also, it will be nice to give some feedback during the pullbacks or move pass. In this example, we modify the camera to simulate pinch, jump, and rotate. Star instantiates an object for us to manipulate. The skyboard gives us some context for rotation. The function getToTouch takes two positions PO and P1, representing the two fingers position on the screen. It converts PO and P1 into VO and V1. The word coordinates get fairly abbreviated frustum depth of 10. The function returns the distance or dis between the two finger positions. This will be used for scaling. The function returns the midpoint of two fingers or mid. Mid will be used for translation. The function also returns the displacement factor or dir of the two fingers. Dir will be used to determine the direction in camera. Mid S, dir S, and dis S are used to store the midpoint, direction, and distance for the star location of the two fingers. When two fingers are on the screen and one finger begin a move, we record mid S, dir S, and dis S. Dis F, dir F, and mid F are the midpoint, direction, and distance for the final location of the two fingers. We obtain these values when either finger ends a move. We'll calculate the scale by subtracting the distance between the starting location from the distance between the final location. When the final distance is larger than the starting distance, scale will be a positive and we move the camera along the z-axis. We translate the camera using the displacement factor formed by subtracting the midpoint of the star location from the midpoint of the final location. However, we need to account for the fact that the world might be upside down. As such, we note the current angle the camera is rotated to. We then rotate the translation factor in the opposite direction around the z-axis using quaternion Euler. Finally, we rotate the camera. The angle formed between the factor formed by the starting finger position or dir S and the factor formed by final finger position or dir F. We obtain the angle between two factors using the principle we saw earlier in the course. We then need to figure out if we are rotating in a positive or negative direction. To do this, we obtain the perpendicular factor using the cross product. If the perpendicular factor points into the screen or positive z, Then the fingers have rotate in an anti-clockwise or positive direction using Unity's left-handed axis system. However, as we are rotating the camera on the object, we need to rotate the camera in the opposite or clockwise direction. That is, clockwise rotation of the camera simulates an anti-clockwise rotation of the Earth. Thank you.